In this demo, we will learn how to set up recurrent neural networks or RNNs. In fact, we'll use them for a slightly non-standard application, which is image classification. To be clear, RNNs are typically used for applications such as text or audio or other time series analysis. But we'll see how we can also adapt them for more conventional settings such as image classification. For this demo, we'll use the standard fashion MNIST dataset, which we've seen several times. This will be a variation called sequential fashion MNIST. So let's start by loading the data as usual. So all this is standard. So this is just building the data loader and plotting a few images from the fashion MNIST dataset. So now, how does an RNN fit into this kind of classification problem? So let's pretend that the classifier has not given the image in a single instant. Instead, one is sort of rasterizing the image. So imagine some kind of raster scan of any given image, and the classifier has to update its class probability as the new pixels come along. So each row is being presented one at a time, and at any given instant, what's the most likely class? Right. So we'll see how an RNN can be used to solve this kind of problem. Okay. So the main thing that we'll understand in this demo is to just setting up an RNN, like what is the way to set up an RNN model and how to train it. So for this, we'll adopt the LSTM model, or a long short-term memory model, and this will have there are two layers with the hidden size 128. Okay, how do we set up this kind of model? Let's set up first an RNN class. So this is a regular neural network class. So as with any other class definition, we need to set up two routines. One is the architecture, and the second is the forward pass. And PyTorch will handle the backward pass for us. So an RNN will have some number of inputs, some number of layers of a particular hidden size, and an output layer which does the classification. So let's set each of these things up. So we start with a super class instantiation. This is all standard. But now let's set up the RNN itself. So we'll have to specify the hidden size. This is usually something, right? So let's just say that it is 128 should be good for this application. So let's do 128. And let's also set up, it's hidden sizes in a variable we pass. Okay, good. So let's just set up the number of hidden neurons in each layer and the number of layers. Okay. And each recurrent unit is going to be an LSTM. Okay. So we'll instantiate this using the LSTM class from PyTorch, which of course has the same parameters. Yep. So one more argument we'll pass into this is what's called batch first. This is because in standard image image classification, for example, the data loaders that we set up here has, if you examine the shapes of the tensors, they're batch spatial index 1, spatial index 2, right? So 1 times 28 by 28. LSTMs have a different indexing structure. So batch does not come first. That batch comes somewhere in the middle, and that's because in time series data, there are two indices you have to worry about. Right? So you have to worry about the batch index and you have to worry about the time index. So batch first equal to true pushes the batch index back to the first as opposed to somewhere in the middle. This is so yeah. Just look at the API of LSTM to see why we're doing this. Okay. Finally, we'll set up a classifier layer. Set up a classifier layer with which will take the hidden state outputs and produce class probabilities. Okay, so this is just the architecture. This is a very simple architecture: 2 layers, 2 LSTM units, and one hidden layer, one output layer, which is classification. Cool. And the next step is to define the forward pass to this model. Okay, so let's say I have an input X. How does X transform through this model? Okay, so here we have initialized the variables H0 and C0. You can think of H0 as the initial state of the LSTM, the initial state of the hidden neurons, and those are typically set to 0. LSTMs also have what are called cell memory. These are implemented in the form of additional gates. So we'll initialize that as well. So that is C0. So how does the output get produced? Well, there is 2 layers of LSTMs. So let's apply the LSTM layer to the input, initialized with H0 and C0. That's it. Okay. And then finally, we need to take the output of the LSTM units and pass it through the fully connected layer. You do a little bit of reshaping here. Okay. Again, this is because of sizing, indexing issues. So we'll do some reshaping and return the output. Cool. So that's about it. This is the structure. This is the structure of LSTM. So let's just see if this runs. Okay. Let's instantiate one LSTM. In this case, the images that we'll feed are of size 28 by 28. So you can think of each token being a row vector of size 28, and there are 28 such rows. So there are 28 tokens in the sequence. Observe, interestingly, that the definition of LSTM does not depend on sequence length. Right? So we don't need to define sequence length in LSTM because by construction, RNNs are designed to handle variable input lengths. Right? So sequence length really does not matter. We do have to specify the number of neurons in the hidden layer and the number of layers. So that's 1, 2, 8, and 2. The 10 classes in fashion MNIST. Let's say we have a batch size of 100 and some other parameters which we'll use in the training. Let's see if this got set up correctly. So we will set up an RNN model with parameters input size, hidden size, num layers, and num classes. Okay. Does this work? Okay, so we now have an LSTM of 2 layers. Okay, good. So let's see if we can train this. But the training we've already done several times. I'm just going to repeat some boilerplate code from before. The main thing to keep in mind in training is that since we're doing classification, let's use the standard cross entropy loss. And for this particular architecture, we'll use the Adam optimizer. Okay, so optimizer, use the Adam optimizer with let's say learning rate equals 0.01 is a good number. Okay, good. So that's all we need to train our model. We need to set up our training loop, which is of course exactly the same as what we've done before. So let's just copy code from a previous project. Like this. So it's just training this for number of epochs. Okay, so it's training the RNN model for number of epochs. So let's just instantiate that and see what happens. Okay, and this will take some time. Okay, so that took about 5 minutes. So let's see how we're doing. You can see that the last started off high, but has come down reasonably well. So we should be able to do okay, I think. Let's see. So this is again boilerplate code for testing. We've seen this several times. So let's not do that. Let's not go over it again. So this just steps through the test data loader and predicts the labels and compares to the ground truth and prints the accuracy. So how well do we do? 87%, not too bad. So this is actually comparable to what we can expect to see from standard shallow neural networks on FashionNest. So an advantage of RNNs for image classification problems of this kind is that these work even if the input is partially available. So for example, if you only have a certain number of rows, so you're rastering an image and you have only scanned a certain number of rows, can you still make predictions of the class? So here's an example of how that will work. Imagine so here I've grabbed an image from the data loader, and let's see how this image looks like. This is just some kind of shirt, and as you can see, the model is predicting the label correctly, right? So it is performing correct classification. But now let's pretend that you can only see maybe you're scanning this image from top to bottom and you can only see 4 rows of this image. So what happens in that case? So now you can see that you're only seeing the absolute top of the image. So it really does not look like a shirt anymore. Therefore, the model is doing poor classification. It's predicting the wrong label. So in fact, it'll be interesting to see how far down we have to go until it actually starts looking like a shirt. Oh, wow. Okay. So by now it's sufficient information here to see that there's a shirt. So yeah, so as you can see this particular example, the correct class label is identified only with like a quarter of the image being visible. So you can play around with this parameter and see for different examples how that would work.